and star people. But I'm here to hopefully clear that up a little bit and make radio astronomy a bit more accessible to all of you. And I'm especially interested in talking to you about what kind of science you'd like to see from radio astronomers, any science ideas that you might have. So please do come and chat to me. I'm really interested in talking to you about what you might want from us. Now, I'm going to present the Sydney Radio Star Catalogue, and I'm pretty sure this is the right crowd to say, if you have a favourite star, you can look up the Sydney Radio Star Catalogue online. If you've got a laptop, it's a bit better on there. So it's radiostars.org, nice and easy if you want to have a look at it right now. So I'm the first radio astronomer in a plenary. So I'm going to say, what is a radio star? So a radio star, as the name suggests, is a star that emits radio light. But then the question becomes, what is radio? Because if you ask there are a few radio astronomers here. If you ask each of them, they'd probably have a different frequency cutoff for what is radio and then what becomes kind of sub-millimeter different frequencies. For me, I'm kind of interested in things definitely below 20 gigahertz, but really the Sydney Radio Star Catalogue at the moment is for things below 3 gigahertz. So that really low frequency stuff. Now, as you can see from this color magnitude diagram, which was made using the Wenke catalogue, and also the red stars there are some ASCAP stars, radio stars across the whole CMD emit radio light. And this includes both single and binary stars. And you can see from this CMD that there's actually not that many that have been detected at those low frequencies, those 3 gigahertz, even 5 gigahertz. A lot more of the stars, particularly up here, have been detected closer to 10 gigahertz. Oh. No, that's okay. Yes, there we go. So if we see a star in the radio, that usually means a couple of different emission mechanisms. So we could have gyrosynchrotron, electron cyclotron maser instability. But what this really boils down to is magnetic fields. So if we see these low frequency radio stars, we're probing those magnetic fields and getting information about the magnetic fields of the stars. So that means that there's a whole range of science that we can do if we can see a star in the radio, particularly if we have lots of detections of it, including dynamo models, magnetospheric topology, coronal mass ejections and transient mass loss, as well as good stuff about ultra-cool dwarfs like electron cyclotron maser instabilities and radiation belts, binary interactions, and hopefully soon, I reckon it'll be really soon, conclusive detections of radio magnetic star-planet interactions. Now you might be thinking, this is great, but radio astronomy is probably the least accessible type of observational astronomy. And don't worry, I understand this. I spent a whole year of my master's reducing LOFAR data, and at the end it still was wrong. So I understand that a lot of people in this room will think that even if you know that your star has been observed by the VLA, the GMRT, LOFAR, ATCA, MeerKAT, those data files are huge. And it takes a really long time and an expert to turn that into something that you can use. And sometimes it turns into something that you can't use anyway. So luckily, the ASCAP telescope, there we go. The ASCAP telescope now exists. So this is the main telescope that I use for the Radio Star catalogue. It's the Australian SKA Pathfinder, and it's 36 dishes spread out over 6 kilometres in Western Australia. That's the side of Australia that nobody lives. And the beauty of ASCAP is that you can observe 288 megahertz anywhere. You can sort of put that 288 megahertz anywhere between about 800 megahertz and 1700 megahertz. But it also has a 30 square degree field of view. So ASCAP can actually do an all-sky survey below 50 degrees declination in a matter of weeks. And we've already done 6. So if your source is below plus 50 degrees declination, we've already observed it multiple times. Whether it's detected or not is a different question, but it has certainly been observed. And this is only the all-sky surveys. ASCAP is doing a whole range of other observations, including VAST, which is the variables and slow transients survey with ASCAP, which has observed large parts of the Milky Way, more than 60, that's 60 times already. And we're going to continue doing that for years. So there's also longer observations, like 10-hour observations. So there's a lot of data, and your source has definitely been covered if it's below 50 degrees. And the even better part of this is that all of this data is publicly accessible, and not just those nasty visibilities that take a long time to process, but also source catalogs. So if your star has been detected, you can download the source catalog of the field and see all of the flux density information, all that good stuff. And science-ready images of all 4 polarizations. So as long as you have DS9 or whatever your favorite FITS image viewer is, you can already download and just open a radio image that's already done. So you don't have to do anything extra to it. So this includes all data that has been validated by the team that's responsible for it. So this includes 12-minute observations from VAST, 15 minutes from RACS, up to 10-hour observations from ENU, who've observed large patches of the sky already. So hopefully this means that you can get some radio data and it's a little bit less scary. Now back to the radio star catalog. Why do we need a new one? So there was one previously, and part of it is because we want you all to be able to use radio data, because there's not that many people do tend to look at radio data. So part of the aim was to make it more accessible. But also the previous Radio Stars catalog by Wenka was last updated in 2001. I was 9 years old, and I realized there could actually be some people in the audience that were like not born then, which is a little bit scary. So it's been a long time and a lot has happened since then. We have so many new telescopes just since 2001, especially wide field telescopes that can do large scale surveys and searches for stars. The Wenka catalog was also a little bit iffy. Now, some of those stars have been classified as X-ray binaries. There's a few things that are a little bit iffy about it. And of course, we want to address even more of those science questions that I already talked about and do some population studies. So at the moment, we don't have any kind of volume limited or not volume limited count of the number of radio stars. What's the population of radio stars? We don't know. Even the kind of types and what their properties are, their flare rates, how does the rotation rate exactly match up? We have some ideas, of course, but we really need a lot more stars. And as you can see from here, for the low frequency stars, we actually only knew about a couple of hundred of them before this catalog. So there's a lot that we need to do and still to do in radio stars. And of course, there are some of these other side quests, impacts on planet habitability. And apparently there are some people who want to get rid of stars from their sample. I've heard about them, cosmologists and stuff. So hopefully they can use this to remove the stars. I don't know why you'd want to do that, but some people do. So what's in the Sydney Radio Star Catalogue? So I'm just going to show a bit of a preview. You can have a look at the paper on the archive if you want to see more about it. But there are 839 stars detected below 3 gigahertz. This more than doubles the previously known number of radio stars. And because ASCAP observes so much of the time, so much of the sky all of the time and keeps observing, more than half of those stars have more than one detection. So a lot of them, if you're looking at the catalogue, you can actually just click a button and see the light curve, the radio light curve of the stars. The brightnesses range from very faint to really, really bright. RPEP is a Wolf-Rayet colliding wind binary. And most of the stars have a Gaia distance, which is really handy for luminosities and things like that. The nearest star is, of course, Proxima Centauri, a well-known radio star. And the most distant star is a Wolf-Rayet that's very far away. Most radio stars are much closer than that one, but colliding wind binaries are quite extreme examples. I don't have time to get into the methods, but come and chat to me if you're interested in that. One of the key ways that we find radio stars, and many people in the audience, the other radio astronomers, use circular polarization searches. And this is because they're only pulsars and stars are highly circularly polarized in the radio sky. So you basically remove all of your sources except pulsars and stars if you look at circular polarization. And we keep expanding. I know we don't have too many stars found with proper motion and variability, but VAST is already finding heaps more stars using variability searches. So this is where all the stars are on the sky. 75% of ASCAP observations are below 0 degrees declination, so it's not that surprising that most of them are below 0 degrees declination. I did include some previous surveys by LOFAR using VLAS and things like that, so there are a couple of Northern Hemisphere ones, but we will be adding more. And most ASCAP observations are below plus 40, though there are those all-sky surveys up to plus 50 declination. This is the first color magnitude diagram I made in my career. I am a radio astronomer. So I was really excited to make this because you can see that there are lots of cool stars. The coolest star ASCAP has detected is the coolest known radio star, a T8 dwarf. So we have M dwarfs and all that stuff right down to T8 dwarfs, as well as giants and subgiants. And so you can see we've got stars across the whole CMD. And I know this is cool stars, but we do have some extreme stars up the top there, Wolf-Rayet, symbiotic binaries and things like that. A whole lot of young stars as well that you can see on here. and one known magnetic CB and two cataclysmic variable, and 2 stars that are Gaia stars that don't really have any other information, but they're in the right spot to be CBs. So we're looking into those. So we plan to regularly update the website version of the catalog. I'm just going to resubmit the paper really soon, but basically as soon as the paper is accepted, I will be adding more stars to the website version. There will be a Vizier version as well, and we'll update that when we have larger changes to make. We have lots of science that we want to do with the SRSC, of course, and I'm very happy to chat to you more about that. We didn't do a full literature search to find all the radio stars that have ever been detected, and this is because there are a lot of papers that are just 1 star and 1 detection, and also I would have to like type out the PDF tables because a lot of these are from like the 80s and 90s, so there's still a lot of work to do to add known stars and literature reviews of stars. We have more searching to do, and as I mentioned, I've already found more radio stars than those 839 that are already in the catalogue, and we're going to do more cross-matching. We need to verify the old catalogue and check those stars and see if any of those are reliable detections. And we've got more polarization searches to do. If you opened it and you're like, my favorite star isn't there, but I know it's a radio star, let me know, especially if you have the radio data so I can add it easily. So I'll finish up there, but if you are interested in ASCAP observations of the SRSC, please do chat to me. And I am especially keen to hear about your science ideas, what you think we should be doing next, what you think we should be adding. So please do come and chat with me. I came all the way from Sydney for this, so please do come and have a chat to me. Thank you.
Time for one question here in the middle.
So because it's below 3 gigahertz, we won't be seeing disks and dust and things like that. We won't be seeing the similar things to what ALMA would be seeing. But if they have non-thermal radio emission from magnetic fields, then yes, because we're not dust obscured at those low frequencies. So they will be in there, but it won't necessarily be from dust disks. Oh, yes.
Hello, thank you. From the CA Paris. Thank you very much. Very good question, easy one, and what is for me. How many stars with planets?
So the question was, sorry for not repeating the last one, is how many stars with planets? Only a couple. So about, I don't remember off the top of my head, I did do a check, less than 10. And most of them are kind of the well-known ones that are well-studied, like YZ Ceti and Proxima Centauri. So those sorts of stars are in there. The problem with this is, of course, these are active stars. So TESS and things like that are specifically not looking at them. We're really interested in that, but I think it might almost have to be the other way around with radio astronomers checking for radio emission from planetary systems. But a couple, not that many, unfortunately.
Okay, let's thank Laura again.